Good morning, everybody. Welcome again for this new colloquium at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Andrea Messinger. He's from the Scuola Normale Superiore in Pisa, Italy. And he will talk about charting the first billion years with the Square Kilometer Array. Andrei will be properly introduced by Dr. Rainer Schredel. Please, Rainer.
Thank you. Good morning, everyone, or good afternoon almost. So many greetings from our director from Anton and from Isabel, from the scientific director of the Severo Ochoa program. Both of them unfortunately cannot attend and send their excuses and best wishes to Andrei. So Isabel has asked me to present Andrei today. Andrei Messinger is currently an associate professor of cosmology at the Scuola Normale Superiore in Pisa. He received his PhD at Columbia University in 2006 and subsequently held several postdoctoral fellowships, for example, at Yale, or had two postdoctoral fellowships at Yale and at Princeton University. Then he moved to the Scuola Normale Superiore. His research was awarded a Hubble Prize Fellowship in 2008 and an ERC Starting Grant Award in 2015. He has written over 140 peer-reviewed publications with an H-index of 51 and edited 2 books. His research interests are first light, reionization, cosmic 21 centimeter, high redshift galaxies, modeling techniques, machine learning, and Bayesian inference. He's deeply involved in current efforts to detect the cosmic 21 centimeter signal and is the current co-chair of the Epoch of Reionization and Cosmic Dawn Science Working Group for the Square Kilometer Array, as well as being an executive board member of the Hydrogen Epoch of Reionization Array collaboration. And today he will talk to us about charting the first billion years of our universe with the Square Kilometer Array. Andrei, it's a pleasure to have you as a Webloquium speaker, and here's all to you now. Thank you.
Thank you very much for that wonderful introduction. It's a pleasure to be here, virtually be here. It's a shame I couldn't be there in person, but hopefully we will rectify that soon, and I look forward to visiting and chatting with you in person in the near future. So today I will indeed be talking about this new potential, the gold mine, the physics gold mine that will be the Square Kilometer Array, and I'll get to why that will be and what we can learn in a minute. And the goal of my talk is mostly to get people excited, get people interested in what will really be a game-changing revolution in this field. So before I get to that, I'll just do a brief introduction about what do I mean, the first billion years, what does that encompass? So I'm sure you're all familiar with the CMB. The CMB is currently the gold standard for one of the gold standards for cosmology, providing us with a measurement of the acoustic, the baryonic fluctuations at redshift of 1100 or so. Which allows us to do precision cosmology, one of the tools that allows us to do precision cosmology. Following the last scattering surface, following recombination, though these baryons were allowed to collapse under gravity, they feel the potential wells that have been established by dark matter, and so they condense into ever increasing structure, ever increasing densities, and eventually, and this is the period called the Dark Ages, the seeds of structure that have formed as these baryons are now allowed to feel the influence of gravity. Eventually, the end result of this process is the formation of the first stars, the first galaxies, the first stellar black holes, and we call this period the Cosmic Dawn. When the first stars lit up, their light spread out throughout the universe in various wavelengths, as I'll touch later on. And eventually they established cosmic radiation fields. This light influenced not only the intergalactic medium where most of the matter resides, but also through feedback processes influenced subsequent star formation inside halos in galaxies. And this period of cosmic dawn culminated in the last major phase change of our universe, which is the Epoch of Reionization, where virtually every baryon in the universe was ionized. And that, we think, ends at redshifts of about 5 to 6. And finally, after that, we have the buildup of more and more complex structures, more and more massive structures, clusters of galaxies, and the zoo of galaxies that we see today. And so the first billion years is this epoch here that encompasses the dark ages, cosmic dawn and reionization. It's mostly the cosmic dawn and reionization epoch, as I'll show in a minute. So you can say, well, okay, what do we know? What's the current status about our knowledge for the first billion years? What do we know about the IGM and the galaxies that formed during this time? Well, we have some indications of this, and this is really driven by observational progress in the past decade or so. And we're now kind of getting a handle on the timing of the process of reionization. And this is a plot of the mean neutral fraction as a function of redshift from one of the latest compendium of constraints. And you can see the midpoint of reionization we estimate to be roughly 7.5, depending on what probes we use. And this is still a very recent, as I said, development, although we still don't really understand the very beginning stages, and we're starting to get a handle on the end stages. But we have an overall picture. You can ask the analogous thing about what do we know about the heating history, right? Gas has an ionization state, but you have a temperature. And this is a similar plot showing the mean temperature, temperature at mean density as a function of redshift. So after recombination, the baryons were thermally coupled to the CMB through constant scattering. But then as the universe expanded, the baryons are allowed to cool adiabatically, become colder than the CMB. And then when the first stars form, actually the first X-ray binary stars form, their X-rays have long mean free paths, and they're able to permeate the IGM, and I'll get to that also in a minute. And these X-rays can relatively efficiently heat the diffuse IGM, bringing the temperatures up to maybe 100,000 Kelvin, we don't know, before the bulk of reionization happens. Don't take these redshifts too seriously. This is just an old preliminary estimate. And reionization then heats the gas to something like 10 to the 4 Kelvin, keeping it there in photoionization equilibrium. Eventually, quasars heat doubly ionized helium, which deposits another boost in energy. But the important thing to note is that we have only observations at relatively low redshifts. The observations that come primarily from the Lyman alpha forest are really only telling us about the late universe, the post redshift 5 universe. The earlier evolution will be probed by 21 centimeter, and I'll get to that in a minute. So we have these kind of rough ideas of mean evolutions of the properties of the gas in the universe, but we really have scratched the surface of this. Right? These periods, the first billion years, are actually the bulk of our lightcone, the bulk of our observable universe. And this is a figure adopted from Professor Chang, and it's actually drawn to scale, so that the surface areas that you see in these rings correspond to the relative volumes that are probed in these redshift annuli. And so you can see that the period in the first billion years above redshift five or so, is the bulk of our universe. And can we really, are those two lines that I showed really the most that we can get from the most of our universe? You know, it's like we're living in this house, and we've seen, you know, the wallpaper on the walls. We see our immediate surroundings, but then we don't see the majority of the house. It's in darkness. Like, are we comfortable with that? I would say no. I think that this is an untapped frontier, and it's inevitable because, again, it's the bulk of our universe. So it contains many very fundamental questions that we have about the birth of the first galaxies. How do they impact each other, their surroundings, the dominant feedback mechanisms that I said, but also dark matter properties. Dark matter provides essentially the scaffolding for the galaxies to grow, and so you know, we can learn about the properties of dark matter from how galaxies evolve, and also in certain models, as I'll show in a minute, that, you know, dark matter can also deposit heat directly into the IGM through annihilation. We can look at other cosmological probes. How does the Hubble parameter, for example, evolve during these epochs? We can study the properties of the first stars, the first black holes, many more questions. And so, as I said, we're starting to scratch the surface. And then the simplest thing you can do if you look at these first galaxies that sit in these first billion years is to do a census. And so you use the Hubble scope to study deep fields, and then you count galaxies essentially at different redshifts. And so after you do that, you get these UV luminosity functions, which are basically just a histogram of how many galaxies per volume you find in a given magnitude bin. So towards the right are fainter galaxies. So the deeper you go, the more you integrate, the fainter light, the more galaxies you find. And if you do just a simple estimate about where do you think this trend will stop, you realize that we're really seeing just the proverbial tip of the iceberg here, right? So we expect galaxies to sit at least down to the atomic hydrogen cooling threshold, which should be somewhere around here. Even before that, molecular cooling can cool gas and let it form stars and even fainter objects down here. And so we're missing the vast majority of galaxies. And we will also, you know, JWST is a powerful instrument, but it won't help us get to the bulk of the population of galaxies. It'll just improve our current limits by something like 1 to 2 magnitudes. And so it's really, you know, the analogous thing you can think of is that if you were an alien and you were trying to learn about humans, and the only thing you could see are the wealthiest humans in existence. And so you could make some inferences. You could you know, postulate that, okay, humans have a head. On average, they have, you know, 2 arms, 2 legs. But you would obviously miss a lot of the interesting nuances. You might incorrectly presume that most humans are rich white males. You would miss races. You would miss genders. You would miss professions, businessmen. You would miss a lot of the details about the bulk of the population from this biased sample that you're getting. And so really, you know, studying these faint galaxies, we need another way to do it. So the route towards progress, well, we can continue learning about the physics of the brightest galaxies, the few brightest galaxies that we see, using JWST, using ALMA, other telescopes. We can continue working on probes of reionization, kind of narrowing down our uncertainties, systematic, to get the mean reionization history, you know, this curve of the neutral fraction versus redshift. But really, the transformative revolution will come from mapping this volume, mapping this first billion years, using the 21 centimeter signal. And from these maps, we can indirectly infer the bulk properties of the whole galaxy population. Okay, so what is this 21 centimeter line? Briefly, The 21 centimeter line is the spin flip transition of neutral hydrogen. In the ground state, the aligned triplet spin has a higher energy than the anti-aligned spin, and this energy difference corresponds to a photon of wavelength 21 centimeter. And so it was discovered theoretically in 1944 and has been used subsequently to map beautiful kinematics of neutral gas in our galaxies, in nearby galaxies, as you see here. But before reionization, our entire universe was filled with neutral hydrogen. And so how to apply this cosmologically, you basically use the CMB as a backlight, and you measure the difference in intensities of the CMB and the H1. And this is in the rest frame 21 centimeter. So it's in the Rayleigh-Jeans tail. So you typically write this in terms of a brightness temperature, because the brightness temperature is proportional to the intensity. And so the CMB photons travel through the universe, and they interact with the neutral gas. And as a result, we see this. We have this. We hope to see something like this, and this will be the unveiling of essentially our Hubble volume. And if you look closely, take a slice through this sphere, and you zoom in, this is what it looks like. So on the vertical axis, you can think of that as an angular scale on the sky, and for reference, this is the moon. So this is something like 8.5 degrees on the sky, and on the horizontal axis, I'm showing redshift, going from redshift 5.5 to 24. And so you can the thing that's striking is the beautiful dynamic range of this image, and the wealth of structures that are encoded in this. So as we go from earlier times, we have these dark ages that I mentioned, but then as the first stars form, you can see how the patterns are where these galaxies are located drive these patterns in the 21 centimeter field, even at very early times. And as I mentioned before, here the gas is adiabatically cool, and so it's seen in absorption against the CMB. And then when the X-rays heat the gas, as I mentioned before, the signal changes from absorption to emission during this transition here, which is commonly called the epoch of X-ray heating, or the epoch of heating. And then finally, the epoch of reionization removes the signal as the universe becomes finite. And so this wealth, this dynamic range is really, if you expand out the signal, you can see it's driven by the fact that the signal depends on various terms. It depends on the neutral fraction, it depends on the matter density, it depends on the temperature of the gas. So it has both astrophysical and cosmological terms, making it a very physics-rich probe. So how do we use this information to learn about these unseen galaxies? Well, taking the neutral fraction, for example, this allows us to learn about the ionizing properties, the UV ionizing properties of the galaxies. And if you look at a very simple example of two extremes, where you have a model, these are from early reionization numerical simulations, where you have a model that has an abundant population of faint galaxies. And here the ionized regions are white and the neutral regions are black, versus just rare bright galaxies, basically the galaxies that we see. You can see the ionization morphology is very different. Here, there are many, many more ionizing sources, and so you have a lot more smaller regions as the H2 regions grow around these more abundant, more uniformly distributed galaxy populations. So even at the same stage in reionization, the morphology is different. But there's also a temperature term. So you can do the same thing using the temperature term. And so you can look at different heating mechanisms and probe the X-ray properties that are responsible for heating the gas. And so if you do a very simple estimate, you realize that X-ray binaries are likely the dominant heating source at high redshift and low redshift. We know that AGN dominate the X-ray background, but as you go to higher and higher redshifts, something around redshift 5 or 6, depending on your estimate, AGN become increasingly rare, and the dominant population that sets the X-ray background are X-ray binary stars. These are stars that grow up in binaries, and one of them is a compact object, and it then accretes gas from a massive companion and emits an X-rays. And so if you take two SEDs, you can imagine we don't really know the SEDs very well of these objects, and if the SED is hard, so that it has more harder, high energy photons, these photons have a longer mean free path. And so you can see that they would heat the IGM more uniformly. This is a temperature distribution if you assume a hard SED versus a soft SED. You can see that the patterns here in the hard case are more washed out. And these differences are detectable, which means that we should be able to also learn about the shape of the SED of these first galaxies indirectly, because we're not going to be able to see them. So there's a lot of wealth that is encoded in this about the first galaxies. The patterns and the timing of this map tells us about these properties, but it's also a hugely data-rich probe, and that's something that really us in the field we haven't gotten comfortable with yet. We're not used to thinking about that. We're used to being data-starved, and you see one quasar and you get really, really excited. But this is going to be a 3D signal with many orders of magnitude more independent modes than for example, in the CMB, which is currently the gold standard in cosmology. So it's going to really drive a big data revolution in the field. And so how do you take advantage of this big data revolution? Well, the obvious thing, if you can do it, is to forward model. The signal and then compare your models to the observation. And so this is something that I've spent the last 10 years working towards. And the goal is to have something like this. This is a mock observation. Again, it's just a 2D slice through this kind of cosmic light cone with redshift increasing along this direction. It's a mock observation, so it's not we don't have a real observation yet, but eventually we'll have a map. And then you need to characterize this observation using some summary statistic. And that's a whole other genre of my research, because there's no obvious choice of summary statistic because it's a non-Gaussian map. So if it were Gaussian like the CMB, you can do a power spectrum analysis and not lose information. This is somewhat non-Gaussian, so there might be better summary statistics. But still, the power spectrum is still an obvious choice. And then you can take this light cone, cut it into chunks. You compute in each chunk a power spectrum, and that's what's shown here. These are increasing redshift, the power spectrum computed from the mock observation. And then we estimate some noise. This is 1,000 hours noise from, in this case, it was from the HERA telescope. And then we excise modes also at large scales that we expect are dominated by foregrounds from our galaxy. And so from this mock observation, you can also combine it with other observations, because this is not the only piece of the puzzle. We also have the UV luminosity functions that I mentioned at the beginning. This is actual data that we have in hand. We also have estimates of the optical depth to the CMB, and so that tells us about the integral constraints of reionization. You combine these pieces to do inference, and so forward model. And so what that means is you sample the parameters that govern the astrophysics of your galaxies, that govern physical cosmology, as well as any residual systematics, and you create realizations of the data. And for each realization, you compare with the observation. And so I have a movie here that shows this, that starts from some initial sampling. This uses the EMC sampler, and you can see just a random sample from the current change shown here with the corresponding power spectrum here, and the light luminosity functions shown here. And so you can see as this MCMC evolves, you can see the posterior is starting to converge. It's bringing up the samples to converge on the observation. You can see visually, in this case, the seed was chosen, so visually you can compare against the mock, but in practice, we use different cosmological seeds when we do this inference. And you can see that at the end, we recover our galaxy parameters here to very high precision, percent level precision. So this is what do we need to actually do this? That I mentioned, this is the goal. Well, there are several pieces to this. Obviously, you need efficient simulations. By efficient, you need to call it hundreds of thousands of times, however many you need for your estimate to converge. And there needs to be parametrized in some way so that you have a parametric model for the cosmology, galaxy physics, and systematics. Obviously, you need observations because you need to compare your theory to the observations, and you need a quantitative way of comparing that. And there's really only one quantitative way, which is the Bayes theorem. One, let's say, rigorous way of doing it, which is the Bayes theorem. So let me go through these kind of steps. So first, we need to simulate the universe. The problem with simulating the first billion years is that there's a huge range of scales involved. So ultimately, we want to learn about the first stars, the first black holes, from cosmic radiation fields. And these are inhomogeneous on scales of 100 megaparsec, 10 to 100 megaparsecs. But ultimately, they're driven by small scale structure, clumps, and stars and galaxies. So we need a subgrid approach. And we do this by cutting off the scales such that on linear and quasi-linear scales, we can simulate things more or less directly. The density field and velocity field are simulated with higher order perturbation theory. And then we have prescriptions for quick radiation field simulation. And then the galaxies and the clumps are simulated using a subgrid, a parametrized subgrid physics. And so the code that we use is called 21 centimeter fast. It's something that I started developing when I was a postdoc. But using these kind of approximate prescriptions, we're able to dramatically cut the computational cost of large scale simulations at the expense of a modest loss in accuracy. So here on the left, you see a mock 21 centimeter image from a hydrodynamic plus radiative transfer simulation. And here you see using the same initial conditions from 21 centimeter fast. And you can see on large scales, and we quantify this in the paper, something like above 1 megaparsec, the two are converged. The power spectra, for example, are converged to within 20% or so. But the dramatic thing is that here you have something like 8 orders of magnitude drop in computational cost in these two things, which means that you can use this for one of these. You can run 10 to the 8 of these and actually map out the parameter space of uncertainties. It's been widely used around the world. It's being used to interpret data from all the 21 centimeter experiments. It's a public code, so if you're interested, you can go on GitHub and find it. The reason why simulating 21 centimeter signal itself is especially challenging compared to other probes is precisely because it is a physics-rich probe. It encodes a lot of physics. And so you start with the density and the matter field, which contains galaxies. And here I show these lightcone slices, but they're inverted so that the redshift increases along this direction. You can see structures forming the cosmic web forming as time increases. And these galaxies that sit in this matter field, they drive radiation backgrounds, and one needs to follow various radiation backgrounds, ionizing for ionization, X-rays for heating, Lyman-Werner, Lyman alpha. And these radiation backgrounds then impact the subsequent formation of galaxies through feedback mechanisms. And ionizing photons, for example, photoheat the gas, making it more difficult for gas to cool and collapse onto dark matter halos, but also photons in the Lyman-Werner band, the soft UV band, dissociate molecular hydrogen which removes the cooling mechanism for the very first galaxies and makes it more difficult for the first galaxies to form stars. And so you can see then at the end, these radiation backgrounds lead to the 21 centimeter signal that looks like what I've showed before. But you can see from this that at different times of at different epochs, cosmic epochs, the structures here are driven by different fields here, which is really the power of this approach. You can see the fluctuations here driven by the ionization fields here. Here you can see they're driven by the very first galaxies, the densities. And so you can see the reason why this is such a physics-rich probe, why so the dynamic range is so large. Just to illustrate this even further, this is a movie from this evolution of 21 centimeter structure progress, which is an ultra large scale public realization, 1.5 gigaparsecs in size. And just to put that in context, this roughly corresponds to the size of the state-of-the-art hydrodynamic plus RT simulation. So we're able to reach much larger scale. And here I show the movie evolving from redshift 35. You can see the global 21 centimeter signal here. You can see the power spectrum in the above panel as structures form, as they heat the IgM, and as they then ionize the IgM, removing the signal. And so then you can ask, well, okay, you talk about these galaxies in a kind of abstract way. What galaxy parameterization are you using? Well, I think there's two things to keep in mind. There is no singular galaxy parameterization that is the right one. However, you're aided by a couple of things. One is that this is a Bayesian framework, so you can change your galaxy parameterization you want and look at like something like the Bayesian evidence to see which is favored by the data. But then the other thing is that the observable signal is actually sourced on relatively large scales. So if I look at one of these light cones with redshift increasing in this direction, and I look at the slice through this is now simulating the resolution of a single frequency slice. So this is on sky slice, using noise as well as foreground excitation. So this is kind of a pessimistic model, but you can still see that the fluctuations that remain, there are fluctuations and they constrain a lot of our physics, but you lose the small scale structure. You lose structure on scales below 10 megaparsecs or so. And what this means is that each of these fluctuations is sourced by tens, maybe even hundreds of galaxies, which means that you can use scaling relations. If you don't have to model individual galaxies, you can use ensemble averages. Whenever you ensemble average something that has a characteristic mean, you have to get, using a central limit theorem, you have to get log normal distribution. And so that's shown here. This is a very flexible parameterization, very simple parameterization of astrophysics, where we take a power law for the stellar to halo mass relation. And in fact, that is what observations see, that there is a power law that has a free parameter which is the amplitude and the scaling. We also take a characteristic star formation time scale, which is scales with the dynamical time of the galaxies. We allow the ionizing escape fraction to again be a power law with the halo mass. And then on small scales, we account for the fact that galaxies have difficulty in cooling and forming stars below certain halo mass with a characteristic turnover. And you can see that these parameters, some of them are already constrained by current observations like luminosity functions. You can't have stealth halo mass relations that are too steep, but then others like escape fraction are only poorly constrained at the, well, at least using this data. And the faint end turnover is not constrained at all. And these kind of scaling relations are just a natural product, as I said, of population averaging, and these kind of models can characterize very different simulations. They all are reasonably characterized by this. This is from a hydrodynamical simulation using very different parameters for star formation. Also semi-analytic models. they result in these power law relations, some observations using abundance matching. They seem to follow these trends. We also need to characterize the X-ray properties, and we do this using the X-ray luminosity, the star formation rate relation, and this is the expected SCD from a theoretical model. And so we have parameters that characterize the luminosity and the shape of this SCD and the self-absorption by the galaxy turnover. And so you can see, as again, some of these parameters are already constrained, others not so much, especially, for example, X-ray parameters, the current observations don't constrain the X-ray parameters at all. I don't know why this is not moving. Whatever. But the 21 centimeter signal shown above does. It impacts strongly the 21 centimeter. So these are the simulations. What are the observations? I showed an example using a mock observation. But actually, we do have some observations currently in hand. Unfortunately, we only have upper limits. This is a compendium of the currently available upper limits from first generation telescopes like MWA, LOFAR, and HERA. And you can see that the limits, this is the expected signal, this is the power spectrum as a function of redshift. You can see the upper limits are still several orders of magnitude away from where we think the signal lies. But we are now starting to get, as time progresses, these become lower and lower as we understand the systematics better. And in particular, I'm going to talk about these two lowest limits that we got recently in pink, and they were obtained by this SK precursor instrument called the Hydrogen Epoch of Reionization Array. It is built in South Africa. This is an actual satellite image. It's not a mock. It's fully built. It's rolled out. It's doing observations using a subsample of antennas as more and more antennas are able to be better characterized and understood. So it's progressing well. And so last year, the collaboration, we published a first results using about 10% of the antennas and using just 18 nights of observations using 4 fields shown here. It's a drift scan telescope. So the sky falls above you and you measure. And these are the observations in red from the different bands. Band 1 is redshift, corresponds to redshift of 10. Band 2 corresponds to redshift of 8. And again, the power spectrum here is relatively large, but these observations are consistent with the thermal noise estimate, which is shown here in black, except for the very large scales where it's still dominated by foregrounds and systematics. And so these we definitely, these are not consistent with thermal noise. So again, there's still 2 orders of magnitude above the suspected signal, but can you say something with this? So that's the question. So you can in fact rule out, you potentially can rule out very extreme models that have very large power. And so what kind of models are the first things that you can rule out? Well, you can look at this equation that I wrote here for the brightness temperature, the signal, and you can go through the terms. This is the ionization fraction, so this can vary from 0 to 1. So it doesn't help us with this prefactor of 30 very much. This is the density field. Again, on large scales, that you measure the density, maybe the tens of percent to something like 2. You don't get much range here. You don't get much of a help here. But then if you look at this temperature term, so here we have the CMB temperature in the numerator. In the denominator, we have the gas temperature, the spin temperature of the gas, which is coupled to the gas temperature. And so when the gas is hotter than the CMB, you can see that this term saturates to 1. But when the gas is colder than the CMB, during this adiabatic expansion, for example, at redshift 10, the CMB would be roughly 30, and the adiabatic limit would be something like 2 Kelvin. So you can get a factor of 15 or so boost from this term if the gas is cold. And so these kind of models, now you're talking, because you have a factor of 15 to help you with this, with the amplitude of the signal. So the first models to be ruled out have to be cold. But these are the models that can get up to those large upper limits. So we require that the gas is much, much cooler than the CMB. And you also need to have, because you're not measuring the global signal, you're measuring spatial fluctuations, you also need to have spatial fluctuations driven by something. So you could have spatial fluctuations in any other term, like the ionization fraction. As we saw, reionization is a patchy process. So you of course have fluctuations in that. You can have fluctuations just purely by the matter power spectrum. And you could potentially have fluctuation in temperature itself, but this is unrealistic because the X-rays generally have long entry paths, and so you can't get sharp temperature fluctuations. You would need a very unrealistically soft SED. And this is an example of what these things look like. For example, this is a slice through simulation where the gas is cold, but you have these black patches around galaxies that have been ionized, versus where the gas is still cold and there's no reionization. And so in this case, instead of these black patches, you have overdensities in the matter field. And so basically this is just a probe of the matter power spectrum with this additional boost in the mean from the coldness of the IGM. And so in both of these cases, the upper limits are exceeded in the power spectrum. But as I started off this talk, we do know already something about the EoR. So this is one of those things, like if the EoR is ongoing, then we can constrain the temperature of the IGM. But we don't have to have that if, because we actually have other additional constraints in the EoR. We know at redshift where the observations are, the EoRs are going. So there are some fluctuations there. So that means that we can actually, not constrain a conditional statement, but actually constrain the temperature of the IGM using this observation. So before everybody gets too excited, it's important to realize that these are still upper limits, as I said, at 2 redshifts and a couple orders of magnitude above where we expect the signal to lie. So instead of what I showed before, it's just kind of these upper limits roughly here. So we're not going to get very strong constraints. But we do get some constraints, and this is the posterior from this from our HERA analysis paper. And in purple is what we currently know using current observations of luminosity functions in EoR history. And in purple is if we add in now these HERA upper limits. And you can see that it doesn't help much except for this one parameter. And this indeed is the X-ray luminosity per unit star formation rate. This is the X-ray luminosity that is doing the heating. And if we don't include HERA, we have a flat prior because we don't have any observations that constrain the temperature of the IGM. But now when we include these preliminary observations, we have this posterior, which is actually disfavoring current observations of local X-ray binary luminosities, which sit here at something like 1.5 sigma. And the reason is that we know that local X-ray binaries actually have a strong dependence on the metalicity of their environment. Low metalicity X-ray binaries have trouble driving winds, and so they have increased mass accretion, and so they're brighter per unit star formation rate. And this is a couple of models for how this should evolve in this low metallicity environment where we expect the first galaxies to lie. So this is consistent actually with what theoretical predictions are, that the first galaxies are more X-ray luminous than local galaxies. I think I'm running a little bit low on time, so maybe I'll speed up. So you can ask, what can we learn using full data, using like a proper detection with 1,000 hours, while you get all sorts of beautiful constraints. All parameters are roughly constrained to % level precision. We detect a faint population indirectly that we don't detect using current luminosity function observations. And the EoR history is almost a giveaway. Like this we constrain it to better than 1% precision, or roughly at 1% precision. So we get a lot of stuff. And the other thing is like the, I've demonstrated this with this flexible galaxy model, but it's important to note that because this is fully Bayesian, you can change the galaxy model, and we demonstrated this in this paper using a more complex galaxy model, and use the data to use the evidence ratios to see if the data prefers a more sophisticated model. And there's so much data upcoming in this that you can have a strong preference, even though by eye you can find very strong degeneracies. The data will allow us to actually infer the galaxy model. So briefly, spend a few minutes, the final minutes, talking about physical cosmology. I've so far been talking about galaxies, but it's also a rich trove of physical cosmology. So the simplest thing you can think of, well, there's this matter term equation, so maybe we can find a cosmic epoch or a piece of the sky where we can probe the matter power spectrum directly. That might be challenging to do a clean signal. So the next thing that you can do, which you should do, is just covary the cosmological parameters in the inference. And you get something like this triangle plot where you can covary both. And if you marginalize out the astrophysics, in this paper, we showed that you could improve constraints on something like sigma 8 from the current Planck prior, the current Planck results, which are used here as a prior. You can get more exotic heating mechanisms. This is a paper computing how much we expect dark matter annihilations to heat the intergalactic medium. And this is a different form of heating than the galaxies, because the dark matter is distributed almost uniformly compared to the galaxy with a bias of 1. And so the heating is deposited in a very uniform way. So it's not degenerate with in the fluctuations, is not degenerate with galaxy heating. And that's something we're continuing also with collaborators, Laura and others, by coupling 21 centimeter fast with dark history and looking at different, looking at how different heating histories can evolve depending on the different annihilation products. Another thing which I think is really exciting is to use, you can use potentially these fluctuations as a standard ruler. So if I run this movie that I showed before, and I stop it at this point, and you look at the power spectrum, you start to, you see some wiggles here, right? And you could say, well, okay, maybe those are cosmic variants, but the cosmic variance sets in over here. These are hugely large. These are 1.5 gigaparsec simulations, and these are 100 megaparsec scale. So what is that? Well, those are actually acoustic oscillations that we see in the signal. So we see acoustic oscillations just come from overdensities in the quantum fluctuations that then in the photon baryon fluid, as it expands, it then ends up stopping at recombination, and that freezes in a certain scale, the sound horizon scale at recombination. And this scale, this characteristic scale, is imprinted in the galaxy formation because it results in a velocity difference between the baryons, which has been dragged along in this fluid, and the dark matter, which has been collapsing the whole while. And you can, this has been noted by Sostrzechowicz and HERA in a paper a decade ago, but simulations have studied this in more detail. And if you look at regions in the universe that have a low velocity offset between the baryons and dark matter, compared to ones that have a high velocity offset, galaxies form much more difficultly in regions that have a high velocity offset, because the gas just kind of streams past and doesn't accrete in the dark matter halo. And so we incorporate this in our simulations, and you can see this characteristic sound horizon scales appearing in the maps. This is a map without velocity, and this is with velocity. You can see these scales, and that's actually what these fluctuations are. These are so-called acoustic oscillations in the velocity offset field, and that are easily measurable, which would allow us to set a cosmic ruler in this regime that's so far untapped during the Cosmic Dawn, and kind of tie in estimates of how H should evolve over cosmic time, which right now, as you know, there's a tension from estimates from the CMB and from local estimates. All right, so I will conclude here. I apologize for running a little bit over time. To conclude, we have this Bayesian, fully Bayesian forward modeling framework, which allows us to on the fly forward model 3D lightcones of various fields, and we can use this toolkit to learn about the first galaxies using upcoming 21 centimeter observations, which will provide us with these fluctuations, these 3D maps that we can compare to our models. And if we look at what we expect from SKA, which is starting to be built, I should mention that SKA has started its construction, and so we expect to get first data within a few years. We will be able to constrain galaxy properties from the patterns in these maps and the timing to percent level precision. But even preliminary data that is 2 orders of magnitude above the expected signal allows us to increase what we currently know. It allows us to consider the heating history during the Cosmic Dawn, and it actually tells us that as we expect, but now we have actual data, the first galaxies are more X-ray luminous than local ones. And this is expected from the fact that they live in low metalicity environments. It also is a probe of physical cosmology. It's a Bayesian framework again, so you can covary cosmological and astrophysical parameters. You could, vary parameters to change the matter transfer function. People have done this. There's a lot of studies in this area that can be done. You can also include exotic heating processes from dark matter annihilations and decay. But you can also find the standard ruler in these measurements from acoustic oscillations that imprint a velocity difference in the dark matter and the baryons. And again, the analysis is fully Bayesian, so you can change your model. You can change your model for galaxies. You can change your model for dark matter. Do the inference and compare the evidences, and you can actually then use the data to learn about the physics, which is going to be a powerful way of thinking about the first billion years. And that's it. So thank you very much.
Thank you very much, Andrei, for this very nice talk. And now the talk is open for questions. Questions will be managed by Teresa. So Teresa, now you are co-amphitryon, co-host here. You should see the raised hand on your screen. So
yes, or actually, let me see here. I'm just going to make sure I can see all the participants. I think so. Okay, I thank you so much, Andrei. This was quite an interesting talk, and I'm going to take the opportunity, because I'm talking, to ask you 2 questions myself, if you don't mind. So I just a comment, there's a lot of H1 expertise here, but mainly perhaps on the nearby universe. So I find it personally super interesting and exciting to see how versatile H1 observations are and how we can use it to constrain the parameters of the Cosmic Dawn. And also very, very exciting to hear about HERA, which is an SKA precursor that isn't always so much in the limelight as, for instance, Meerkat and so on. So one of the things I thought was really cool is when you're mentioning, oh, you just need to simulate the universe, and it sounds like quite a task. And I remember in my PhD studies, I was modeling the H1 contents of galaxies, and I felt super cool when I was doing this. So my first question was just really, what kind of data power do you need to simulate the universe, to model the Cosmic Dawn H1 content? And you mentioned briefly this 21 centimeter fast, and I saw a slide of network of stations, but I missed that a little bit. So
yeah, so I mean, the idea is that we have these kind of approximations that we make. And so, for example, the matter field you can do quickly using 2LPT, because again, these are scales that you observe are scales on relatively large scales. You're not observe directly galaxies, you observe fluctuations on 10 megaparsec scales, or maybe a few to 10 megaparsec scales and above. So 2LPT is perfectly fine. But then it's the radiation fields that end up being more challenging, and you can't afford to do radiative transfer. Instead, what you can do is you can do, again, averaging over spherical shells in kind of the light cone. And you can say for each gas element, you can count the emissivity in certain shells surrounding that gas element. And you can actually store that, because these are just FFTs, they're quick to evaluate. You can store that in memory. There's a lot of efficiency hacks that allow us to compute this in a reasonably quick way. And so, at the end, you can do one of these realizations roughly in 1 hour if you do like a good resolution simulation on like a single core, which is not bad, but it does mean that to do like 10 to the the inferences that I've shown were done with something like 100,000 or 10,000, well, 20,000 live points, 100,000 samples, something like this. You do need a cluster, and you need a couple of weeks on a cluster to do it. But still, you have 100,000 then samples from a posterior of a universe, which then is great. You can post process that to do machine learning. We're doing that actively, and various other things.
Okay, that's awesome. That's impressive. Actually, could I ask you to maybe unshare your screen? It will be easier to see everyone.
Sorry.
There we go. And see raised hands. So I do have another question, but I actually always ask every co-chair of a SKA working group. And it's the SKA is kind of famous for the ability of commensal use of the data. And maybe I should have warned you about this, because people are usually more into your own use of the data. But do you know anything about how the upcoming data that you would use for this research might be used in other areas as well?
Well, yeah, I mean, the raw data is well, not the raw data, but some version of the process data is going to be shared. So the stuff that I was showing will come from SK Low. SK is already used by other groups like Pulsars, or Cradle of Life, and others. And so there are some commonalities in how the data is processed. So some of the data products will be publicly available, and other research groups can use it. From our end, we tend to make everything public. So the codes are public. The posteriors are public. People are welcome to check the research that we did using their own tools. So there is kind of a philosophy of making things public as much as possible.
Okay, well, thank you. Do we have any other questions here? I'm unsure if I'm actually seeing everyone. No other questions? I think you're going to have to yell them out if you have one, because my screen seems weird. And if not,
there is Rainer.
Oh, yes. Hi.
Sorry, I have a question which is kind of really on a side topic here, since I'm not into 21 centimeter, etc. But I missed again would you kindly repeat the explanation why metal poor X-ray binaries are more luminous than metal rich X-ray binaries, Andrei?
Yeah, so that's an empirical observations. I can show the slide that shows this. It's empirically observed in local star-forming galaxies. Let me find the slide to show the data. But it's theoretically also expected from people that do modeling of the first. Why can't I find this? That do theoretical models of X-ray binaries. And the reason is because you have inefficient winds. When you go to low metallicity environments, you have a less mass loss because I can't find it.
Okay.
But you get less mass loss because the metals help couple the radiation pressure.
Right? You refer to mass loss from the accretion list, not from the companion.
It's from the companion. So the companion object ends up with low metallicity, it ends up preserving its outer envelope because it doesn't have the metals to drive winds, because the metals are required for efficient coupling of the radiation pressure that pushes out the winds. So the companion ends up being more massive. It has more of its atmosphere that then gets dumped onto the binary.
That is true for massive X-ray binaries, also for low massive.
Yes.
Massive X-ray.
For massive X-ray binaries. The low massive ones take a long time for the companion to evolve, and they dig in later. I have another plot of that I can.
Now I get it. Thanks a lot.
Okay.
Thanks a lot.
All right.
Anyone else? If not, I'd like to say a big thank you again for giving this presentation, and found it very illuminating. And I'll hand the word over to René again.
Thank you.
Thank you, Teresa. Thank you, everybody. Thank you, Andre, for this talk. And
thank you.
Everybody, see you tomorrow. We have another talk by Jose Luis Gomez, and he will talk about the new image of the black hole. Thank you.
Thank you very much. And take care.
Bye. Thank you.